Sigrid Close, Professor, Department of Aeronautics and Astronomics, Stanford University, talking about meteoroids hitting the glass. Well, she doesn't know it's glass, but I'll show you in a minute that it is glass. Atmosphere at 100 kilometers high.
Have this continuous rain down on the Earth. So actually, every morning at 6 a.m., as the
Earth is in orbit,
it's plowing up this debris, just like a bug on a windshield effect. Just like a bug on a windshield effect.
Just like a bug on a windshield effect.
Bug.
And you will see, as I mentioned, billions of meteoroids.
Why is that?
In a second, if you're using
Why is it hitting a bug on a windshield?
These plasmas are formed between about 70 and 140 kilometers. Just so happens that that's the right altitude. There's enough neutral densities, but it's not too low down that the meteoroids have burned up. So there's a sweet spot in the atmosphere, and that's why we usually...
There it is. Thank you, Sigrid.
Still enough energy associated with the meteoroid to actually 100
kilometers. Sweet spot.
We can determine things like what's the neutral densities at 100 kilometers altitude. We can determine things like what's the neutral densities at 100 kilometers altitude.
Neutral density filter. In photography, you know what they're made out of? That's right, they're made out of glass. Neutral density filters are there to actually attenuate or minimize the light and even it out, but they're made out of glass. Interesting, very, very interesting. Here's another website talking about neutral density filters. Yeah, made out of glass, guys. There's a glass sky above us at 100 kilometers. We're inside the Earth. This poor woman, she doesn't even realize it, but her handlers do. Her higher-ups at whoever, not a straight answer, or Stanford, they know. They know there's a glass sky. Look at that, neutral density filters made out of glass. Whenever she says neutral density, she's talking about the glass sky at 100 kilometers. There's another one, square optical glass, neutral density filter. Let's listen to her again.
But what happens is it's a pretty simple process. The meteoroid comes in, if you'll forgive this little cartoon, it heats up and it sheds off ablated atoms that then collide with the background neutrals.
Collide with the background neutrals.
And forms a plasma, which is just the ions and electrons. So what most people don't understand is that when you use radars to detect meteors, but if you look at this movie, you'll see that this is actually the meteor. This is the plasma formed when the particle comes in, hits the neutrals.
It's the glass, you mean?
So you're looking at how much energy is released upon each
impact. Did you know that?
Turns out it's on the order of about 6 eV or so.
When light hits glass, it gets ionized, especially ultraviolet light.
So if you take it over how many impacts occur each time the meteor is traveling in space as it hits all these neutrals, it's on the order of about 600 eV. Okay, 600 eV per
glass
molecule released. Huge amount of energy. Most of that energy goes into actually ionizing itself as well as the background neutrals.
As well as the background glass.
If you happen to be sitting at Altair, this is what you would see if you would look up at any point and go in the meteor regime again, remember about 100 kilometers. So what you're going to see here is just a movie of a meteor coming through. This is the VHF, very high frequency, and this is VHF, ultra high frequency.
Look at that horizontal band. That is the glass sky.
So as you see, it came
100 kilometer level.
Deposited some plasma there, and you see some spikes going up and down. On the bottom, again, is the UHF, and on the top is the VHF. So just from observing this, you can see that it has a really strong frequency component. Depending on what frequency you're using to radiate it, you'll get a much different response. So this VHF trail goes on forever, the UHF disappears. But the meteors reside in that central part near 100 kilometers. The meteors reside in that central part near 100 kilometers. So a real-time snapshot of that movie that you just saw here. This is what's called an RTI, range time intensity profile. On the y-axis is altitude or range.
Straight horizontal line.
And it's color-coded.
At 100 kilometers. Okay, maybe it's about 101 kilometers, maybe.
And as you can see here, this
101.1 kilometers
is the head echo. That's the
how the heck can we get a straight line like that, guys?
What's so great about head
unless it's a hard surface,
with the velocity
like
of the
glass,
so
like a bug on a windshield.
Observable on the meteoroid.
Like a bug on a windshield.
But as you could probably see just from this image, the signal strength is really
like a bug on a windshield.
So you need something like an Arecibo to be able to detect it. On the right, extending from the head, is the trail. And these are stationary, or they move with the velocity of the neutral winds. So think 100 meters per second or less. So the head echo is going 60 kilometers per second. The main velocity of the trail is due to basically atmospheric parameters. But they're much easier to detect. So there's a combination. There's something that's really hard to detect but gives you more information, something easier, but there's a lot more modeling to try to get out the parent properties of the meteoroid. Some of these dusty trails, so this whole area of dusty plasmas, can go on for many minutes, sometimes even hours. So when they linger that long, they create something called a sporadic layer. It's a dense
100 kilometers. Sporadic layer. I think we have a winning combination here. Sigrid, this is a call out to you. Watch this video and become illuminated. You're living inside the concave Earth. Here's another graphic. This is from a website that talks about the equatorial electrojet and the ionospheric modeling. And just this particular graph caught my attention. Look at that. Look at the bottom line at the 100-kilometer level. It's going straight across. There's definitely a hard barrier at 100 kilometers. It's right there, this range time intensity plot of received power from Jicamarca radar facility in Peru at 12 degrees south latitude. So, that's right there, guys. There's so much proof and evidence that there's a glass sky. I'm going to put links in my description box. I have probably about 50 videos talking about the glass sky at 100 kilometers high in the concave Earth. Please watch them. I'll even make a playlist out of that and realize that we have a glass ceiling above us with ice attached to it. Thanks for watching.